Welcome to Maths with Bob. Today we're going to look at a minimizing problem about finding a minimum time from an island. We're going to go from an island over here, and we're going to row a little while, land on the beach or the land for a while, somewhere along the beach, and then we have to go walk along to a hut over here. Okay, now we're just going to watch a little video, just a demonstration from GeoGebra for a little minute, and then we'll come back. Okay, well this is a demonstration minimizing time. The situation is we're off in the sea in an island S. Let's have a look, where's S? S is over here. Okay, 10 kilometers perpendicularly from the land. And there's a hut 20 kilometers along the beach shore, along the land's edge there, out there, over there. And we have to try and work out how we can get there the quickest way. And we can row, obviously we're in the sea for a while, and then we can walk. We've got a couple of legs. You can see here I've actually got a time function as a function of x actually. And there are a couple of things. I can actually change my, this is the situation we're going to be dealing with shortly with calculus. You can see I can change my velocity, and I can actually change the function, but I'll leave it at 6. I can change my rowing velocity as well, but we'll leave it as 4 because this is the ones we're going to be looking at in the problem. Now we can change over in a few different spots. I can actually adjust the changeover. You can see here, you can see the time 5.22, 5.25. This is at 6, 8. You can see out here 12, 14. Okay, 5.3 hours, 5.4. Okay. Okay, about 5.48. Let's actually come back and have a quick look. 5.2, 5.2. Okay, all right. So somewhere between 8 and 10 is probably the ideal crossover spot, but we don't exactly know where it is. But let's actually, first of all, we'll look at calculus and try and find this out. Okay. Okay, well, welcome back. Now, how do we set this problem up? Well, the first thing we have to do is we have to sort of say, well, let's let this distance here, say, be x. And this one would be, say, 20 minus x. Okay, he's walking 20 minus x kilometers. Okay. Then we have to sort of think about velocity. Now, we know that velocity is what? Distance on time. Therefore, time is actually what? Distance on velocity. Okay. Now, the distance is a function of x, and the time is obviously going to depend on the velocity. So we're going to set up a time function to minimize. Okay. So the first thing is we're going to row. Now, you can see there that rowing would be, okay, there's a Pythagorean result there. So, okay, row would equal what? Distance would be what, the square root of 10 squared plus x squared. Okay, so we'd have to row that distance, and we'd have to walk 20 minus x. So the times, okay, would be what? Let's have a look at the time. So the time would be, for the rowing section, would be what? The square root of 10 squared plus x squared on the velocity which we're rowing at. And remember, we set that up at 4. And, okay, the distance we're going to walk, well, that'll be 20 minus x, and that would be all over 6. So we're walking at 6 kilometers an hour. So this is a time function as a function of x. Okay, that was the blue function on the demonstration. Okay, so what we have to do is differentiate now. So we need to actually work out, okay, dt dx. So we have to differentiate this, and we'd write this as, okay, now this is, okay, we need to write this expression here as 10 squared plus x squared to the power of half. And we need to differentiate that, so we have, what, a half, okay, 10 squared plus x squared to the negative a half, okay. Now this is a bit a lot of people forget. Now we have to multiply by the derivative of what's inside the brackets. This is the chain rule by 2x, and it's still all over 4. It's all over 4, and if I differentiate 20 minus x on 6, well, that just gives me a negative 1, so it's actually minus 1 on 6 here. Okay, and then we'll set that to equal 0 to try and find the stationary value. Okay, so let's have a look. Well, one thing happened. Well, first up, we can cancel a couple of 2's. Okay, let's have a look. Okay, so let's, okay, put the 6th on the other side. So 1 on 6 would equal, let's have a look. There's going to be an x on the top over here. And if I put that square root on the bottom, we get what? 4 lots of the square root of, say, let's call it just 10 squared now, so 100 plus x squared. Okay, so we have to try and solve this equation for x. Okay, if we cross multiply, you can see here we'd get what? 4 lots of the square root of 100 plus x squared. Okay, that would equal what? 6x. Okay, then we divide by 4. Okay, what we get 6x on 4 is equal to the square root of 100 plus x squared. We square both sides, therefore we got 36x squared on 16 equals 100 plus x squared. Okay, so if we take off x squared off both sides, we end up getting something like this. We get 20 on 16 lots of x squared is equal to 100. Rearrange this and we'll end up getting what? Okay, I think it's x is equal to the square root of 80. Okay, which is roughly about, worked out about 8.9 kilometers along the coast. That's roughly where we'd land. Now, we actually want to find out the minimum time. Okay, so now, is this a maximum or minimum? Okay, well, if we look at this, we should actually verify this, but I'm not going to verify it in this situation. Okay, how would you verify that that's a minimum time? Well, you could either find the second derivative, which we could do actually, or you could sample the slope on either side to show it was actually was it negative 0 and positive actually through this value of square root of 80. But we're now going to substitute square root of 80 in for the time expression and try and work out what the minimum time is, just to have a quick look. So if we put in the square root of 80 for x, okay, so the time would be, let's have a look, the square root of 100 plus, well, x squared is actually 80, plus 80, all over 4, and then we have a 20 minus a root 80 over 6. This turns out to be about 5.1967 hours, so about 5.2 hours to 1 decimal place. So this is roughly about 5.2 hours. This is to 1 dp. Okay. Now, just to verify that this is actually a minimum time, I thought I would show you how to minimize, well, actually to demonstrate it is a minimum. Okay. So if you look over here, I've actually got the derivative, dt dx, and we're going to sample the slope. Now, the second derivative would be a bit messy, okay, but I think if we could just sample the slope, let's actually try and sample the slope, okay. Say, okay, a little bit before root 80. So let's actually say, so before, okay, say at x is equal to root 70, and let's look a bit after. Okay, x is equal to, say, root 90. Okay, now what would you do? Well, you'd put this expression in to the derivative. Okay, so therefore you'd have a look at what, okay, the square root of 70. Now this becomes 100 x squared to be 70, so it'll be 170 to the negative a half all over 4 minus 1/6, and you try and work out what that was on the calculator, and it actually works out to be negative roughly 0.006. Okay, so it's negative before. Let's look at a little bit after. Well, we know it's 0 at root 80. So let's have a look at root 90. So root 90, okay, then we have a 90 here to the negative a half, and we sub it in on 4 minus 1/6. And if we look at that and put that in the calculator, we end up getting positive 0.005. Okay, so at that value, x is equal to root 80, we have a slope change of the gradient, if you like, around it at negative 0 positive. Okay, negative 0 positive, yes. So therefore, this is actually a minimum time. Okay. Okay. Well, thank you for watching, and we'll try some more maximum and minimum problems shortly. Bye for now.